Well, I think we can start officially. Welcome back, folks. We're on week 8, midterm week, so congratulations. After 50 minutes goes by, we're 50% done with the entire semester. Big things that are going to happen this weekend are, well, probably Friday, not quite on the weekend. On Friday, I'm going to start grading the exam 2. And when I put in your course grade on that exam 2, that's essentially just going to be your midterm grade. So it's going to include the average of exam 1, exam 2, all the homework up to section 6.3. That'll just be rewritten as your midterm grade. I'll make a new grade entry in the Canvas system that you can check under here for that midterm grade. So I plan on having that graded sooner than later. I have a math department meeting on Friday that's going to cause some problems, but it's only an hour long, so I'm going to try to get it done before noon. If you don't see it at noon, it's probably coming in sometime before 5 p.m., but some way, somehow, that's my goal for Friday, getting through the grading in this class. Then after that, we're going to be working in section 7.1. The due date on this one is kind of far out. I'm not going to try to finish this section in one day. This is a pretty large section, but this is going to be our goal for today's work, making some decent headway into section 7.1. And we might look into this file a little bit, avoiding circular logic. It sounds exciting, but it just depends on how far we get into 7.1. Well, any questions or comments at all, folks, before we get started today? Okay, well, let's jump in. 7.1 is our goal to collect lots of trigonometric identities. A trigonometric identity is just an ordinary equation like these that are true for all values of the variable that are in the domain of the function. Domain of sine and cosine is all real numbers, so this identity is true for every single value of theta. These are a little bit trickier because this involves a cosine in the denominator, and so does this one. So this identity is true for all values of theta for which we don't have a 0 in the denominator. Say you can't put in a pi over 2 here, for example. Cosine pi over 2 is 0, and secant squared is just 1 over cosine squared. Doesn't matter if you square your 0, that thing is still undefined. So all values for the angle theta in the domain of these functions that we see, these are statements that are always true. So that's our goal in section 7.1, collect as many trigonometric identities as we've seen before and see how to start to use them. Chapter 7 is all about trigonometric identities, and then in chapter 8, we'll apply them into other kinds of applications. First, before we just jump into the problems, it's good to pause and just reflect on why this one would be true. The connection comes from the unit circle out of nowhere. It's back from chapter 5, section 5.2. When we draw this diagram, it came from the equation x squared plus y squared equals 1. And this is what we use to define a trigonometric identity. We picked an angle theta. So let's let theta be this angle. It causes an intersection on the unit circle. And so there are some bona fide coordinates here, x, y. I can tell you for sure x is negative, y is positive. But the idea was x is defined to be cosine theta. Y is defined to be sine theta. And so you can just completely re-express the equation, x squared plus y squared equals 1. In place of x squared, put in cosine squared. So that's why that's part of the identity. In place of y squared, put in sine squared. It's kind of curious the order is flipped, but with cross addition, you can put these in any order you'd like. And that's why this identity is true. It came directly out of the unit circle. Then you can do all sorts of things with this identity. I think we briefly explored if you divide this identity here by, say, cosine squared, you get this one. Let's look into that just briefly. Take the original identity, sine squared plus cosine squared theta equals 1. Divide the whole thing, I think we said, by cosine squared. Then you would have right here a cancellation. This is just 1 plus, excuse me, let me try again. That's the cancellation on the right-hand side here. Back to the drawing board on that. We have to recall that tangent is sine over cosine. So right where that dot is, that's tangent squared plus a 1 on this one equals 1 over cosine of secant. So the right-hand side is just secant squared. Forgot the input variable, theta, on both of those. And that's where this identity comes from. Same trick gives you this identity. You're just dividing by sine squared instead. So these three identities are referred to as the Pythagorean identities. In a real sense, they're the core identities of trigonometry themselves, because they came directly out of how we even defined a trig function, sine and cosine. Well, any questions, folks, about that grouping of three identities there? Okay, other things we looked into were odd versus even functions. So those are these identities below. We looked into periodicity. Periodicity just tells us that the functions repeat. That's what we were seeing on the graphs when we were working with them. As an equation, it would look like this. If k is any integer, maybe say 1, then the value of sine repeats because it has period 2 pi. Then sine x plus 2 pi would just be 1. If k is, say, -2 or +2, same idea, just any integer k whatsoever, you have these kind of cancellations. The period of sine, cosine, cosecant, secant was 2 pi, but the period of tangent and cotangent is pi itself. That's why there's just a pi k here, pi k there. Then the next things are just the reciprocal identities versus the major identities on the left here. If we call sine theta y, cosine theta x, tangent's just sine over cosine, and then everything on the right-hand column is just the reciprocal of the functions on the left. So this is our write-up of identities so far. We haven't looked into a lot of identities, but these would be considered the major core ones. We'll be using the Pythagorean ones quite a lot. Periodicity are just mainly here for the completion. We'll use even and odd identities occasionally, but we'll also use reciprocal identities a ton as well. So with all these in mind, let's try these out on the problems below. Every time I use an identity, I'll be sure to write it down. And I encourage you to do the same, whether you're doing this on Scratch work or doing it for a homework assignment. The more you write these down, the more the mental connection it makes, and the easier it is to memorize these for the purposes of the exams. So here's what we're going to be doing with identities. First thing we want to do is just simplify expressions, which is a natural request. In any kind of math class you'll take after this, you can see these kinds of things as outputs to some other mathematical topic or process. And you always want to try to make these things as simple as possible before you maybe work with them in some other step. Or maybe we're in section 7.5 and this is equals 5. If this is a trigonometric equation, you definitely want to simplify it as much as possible before you try to go and find solutions for x. So the first core thing we do when we simplify identities is try to write things down in terms of sines and cosines. We'll look into other tricks, but that's one good idea. So write expressions in terms of sines and cosines. So that's our first big identity. We're not sure if a trigonometric first big idea. If we're not sure how a trigonometric identity can be used right away, that's the first thing we'll go for. And maybe another thing we should watch out for is that negative x is a problem. We want all inputs to be identical if possible. We'll see how to handle that if it's not possible. If there's, say, a cosine 2x here, we'll see what to do with that in the next sections. But this is a problem. If there's a negative x and the others are x and x, then we need to use the even odd identities to fix this. Let's actually take a look into that table one more time. The cool thing about the even odd identities is this is the odd one out. Cosine of a negative input just gives you cosine theta, and secant is just 1 over cosine, so it does the same thing. Cosine of negative theta, you just essentially delete the negative sign and get cosine theta, same as secant. But for all of the other trig functions, a negative here gives you a negative on the outside because the rest of them are odd functions. So the even one is cosine. The odd ones are everything else. That really helps a lot with memorization. So that means down below here, that's an odd function, and we can just rewrite this as equals cosecant x. The negative sign that would have been here, I'm just going to write out in front, cosine x, cotangent x. So I haven't done this step yet, right, in terms of sines and cosines, but at least all angles are identical. They're all just x, x, and x, all inputs to the functions. Any questions first, folks, on using the even odd identities there? Okay, well, here's our next step. Cosecant can be written in terms of sine. That's just 1 over sine. Minus cosine x is already written in terms of cosine. But cotangent x is just cosine divided by sine. So go times cosine x, divide by sine x. Our goal is to simplify this, and it looks worse, but sometimes that happens. Sometimes things get messy before they simplify. The thing to note is we have two fractions now. This is just a cosine squared in the numerator of this one on the next step. And we also have the least common denominator for free. This is 1 over sine x minus cosine squared x over sine x. So all we've done so far is move a negative sign out, re-express cosecant and cotangent in terms of sines and cosines, and cosine times cosine is just a cosine squared. Any questions to this step so far? Okay, well, like we mentioned, we have the least common denominator, so we can just add across the numerator straight out. This is sine x dividing into 1 minus cosine squared x. And this isn't exactly simplified, but it's starting to look better. I mean, it was better than this line here, the third equality. But it's really, in a certain sense, not all that much simpler than this. Here's where we get to use an identity. So we have three big ideas that we're using. Write things in terms of sines and cosines. Make all the inputs the same. The next big idea is use trigonometric identities. And there's one looking right at us. It just isn't always easy to spot. Anyone happen to know which identity we could use at this step here? Would it be cotangent? Not quite a cotangent identity, but there's going to be an identity involving cosine itself, it turns out. So the identity, again, it's kind of hard to spot because if you think of what was the identity involving cosine squared, doesn't seem to be anything here except that, you could solve this one for cosine squared. That one identity has three different forms. When one is solved for on one side, when sine is solved for, and when cosine squared is solved for. This one has three forms and this one has three forms. You're really looking at 9 identities all at once. The hook is, if you see a sine squared or a cosine squared, try this out. If you see a tangent squared or a secant squared, try this one out. And likewise, if you saw a cotangent squared or a cosecant squared, try this one out. So let's bring down this Pythagorean identity. Again, it's tough because we're training our eyes to spot when it's going to be used. And here's the big use. Cosine squared theta plus sine squared theta equals 1. It's okay to use theta, but it probably feels more natural if we use the same variable, x. And, if you solve for sine squared here, you can say that sine squared x is 1 minus cosine squared x. And that's exactly what we're looking in that numerator. So we can just make a big swap, 1 minus cosine squared, for sine squared right into that numerator. So now we have sine squared x Now it's starting to look like it simplifies a whole lot, right? This is sine squared x divided by sine x. Using properties of exponents, sine goes into sine squared, leaving sine. So this entire original mess, cosecant x plus cosine x times cotangent negative x, was just a clever way to write sine x in the end of the day. This is one way to do it. If you did this as a homework problem, you might have taken a whole different approach. Some people might have said, solve for cosine squared, substitute back, and there might be extra algebra. And you might have found some other approach that I just didn't see looking at it the very first time. But any questions at all, folks, on this simplification here? Okay, one down. You know, when you look at all this, the equalities are equally important to the whole process. What we said is, if this is equal to this, which is then equal to this, and so on down the line, then we have proved something. We just showed, you don't have to write this in the homework, but it's a good thing to reflect on. We have shown that cosecant x plus cosine x times cotangent negative x equals sine x is an identity. We proved it ourselves from scratch. We didn't know where we were going with this. We just simplified until we got down to something nice. Let's try it again on part B. It looks a lot worse, but the same ideas apply even to this one. Let's put on another, well, maybe we can fit this in. Now let's go for another page. There's no reason to cram it in. First idea we want to think about is we want all the inputs to be the same if possible. And so this negative x does present a bit of a problem. But it's okay because we can use the even odd identities and say that sine negative x is nothing but negative sine x. We'll just output an extra negative sign going in front of that negative sign. So it'll be a negative times a negative. Let me write it in this way so we can see it actually happening. Here's the negative, here's the extra negative. All that's left in the numerator, let me try to write that again, is sine x, cosine x, secant x, cosecant x, tangent x, cotangent x. It's a lot of copying for moving around a negative sign. So now by negative times a negative, this whole part's gone. We'll draw parentheses. And now we need to do something else to this. You know, there's an immediate cancellation on this one as well. Recall that secant is just 1 over cosine. So this is just a cosine times a 1 over cosine. There's an automatic cancellation right here. We'll write it in on the next step just so we can visualize that. And same idea, there's a sine times a cosecant. That's a cancellation. And it gets even better because if there's a cotangent down below, you can do this. 1 over cotangent x. This is the whole reason we have a fraction. But if we just move that up into the numerator, that's possible because the reciprocal of cotangent is tangent x. So we could just move that up and put tangent x up into the numerator position, just losing the whole fraction bar in one step. So taking this into stages, let's fix at the secant, cosecant, and also move cotangent. We'll have a sine x times a cosine x times, let me get my colors going, 1 over cosine x. So fractions are back, but very briefly, 1 over cosine was the secant. Cosecant is 1 over sine. Then it was a tangent x. And out of the blue is another tangent multiplying this. So we have tangent times tangent x. Not really out of the blue. This just moved into the numerator in that way. So this gives us fast cancellations. Cosine and cosine cancel. Because multiplication is commutative, you can switch the order and just bring sine up in front. But really, this is just a 1 in the middle as well. Either way, because there's just multiplications all the way through, we can cancel from here out to here. All that we're left with is just tangent times tangent. So it's a tangent squared x. At that stage, we're done. We could use an identity because we know tangent squared x plus 1 is secant squared x. That's not going to simplify it, though. I think this is the most simplified form for writing tangent squared. You know, it might have fit on the last page. Let's bring it up just to keep the file shorter. Also, to compare what we did on the last one, one big idea with part B is you can't really tell just by looking at the problem, unless you're really good at eyeballing it and seeing the next several steps. It's not easy to see if this was a hard problem or this one was the harder problem. This one looks shorter, but it was actually more involved going through the steps. This one looks like a gigantic mess, but it just cleans up immediately and rapidly. So that was part B on this one. Any questions at all, folks, on what we've done so far? Okay, we've used several identities so far. I'll keep on writing the identities on the right-hand side as we're going through these. And for the next one we'll look into is simplify with an extra set of instructions. I only wrote or only assigned one problem like this out of the book for section 7.1. It's kind of an interesting problem because when they say write your answer in terms of secant x, it's a little bit more information than what this was telling us. This just said simplified. We didn't know what we were going to land on, especially the last one, which felt like a big adventure. We didn't know we were landing on sine x. This one's telling us that when you simplify, the only trigonometric function that should be left over is just secant. It could be 5 times secant. It could be secant all alone. Writing in terms of secant x just means that's the only function we should see. So it's kind of helpful to see it that way because it gives us a direction to go this time. Next thing we have to do is just figure out how to get that to happen. Let me hide the next problem. So it's cosine divided by 1 plus sine x plus tangent x. Let me just start by copying that in. Cosine x, 1 plus sine x, plus, I know one thing we can do with tangent x is just write that in terms of sine and cosines. So tangent is a sine x divided by cosine x. And that's what we have. There's no apparent identities that we can use it on this at all in this format. I can't use a Pythagorean identity because those involve powers of 2. And sure, you could say solve for cosine and square root something, but you need more information to know if you're dealing with a positive or negative root, what quadrant the x would terminate in, for example. So this one's a hard one to determine where to go. But the next big idea is if you see a fraction, add them up. Oftentimes, that's something to try. So if fractions come up, add or subtract, depending if it was a minus sine x over cosine x, the fractions. We've actually done this once, example 2 part A, but this is less convenient because now we need the least common denominator. So this is a bit of an algebra review in and of itself. It's not as bad as it seems. It just looks messy at first, that you can kind of tell by the size of these bars we're putting in. It's kind of a game of just matching things up. So I'll first write in cosine x. And then in parentheses, 1 plus sine x. Then the next one was sine x over cosine x. For least common denominator, the first thing you should be thinking of is we want a common denominator first of all, and then we could worry if it's the least common denominator afterwards. So we just want to force the denominators to look identical. We ask ourselves, in this denominator here, what is missing? Exactly, we just need that cosine x, as was said in class, so we just write it in literally. Cosine x here, cosine x here. That's allowed algebraically because this would cancel off, getting back to the prior step. We don't want it to cancel off. We want the denominators identical, so it has to be more complicated before it gets nicer. And then just do the same step again. This one is missing 1 plus sine x, so we write it in. We now have to put it above and below. Now the denominators are identical. That parenthesis there around sine x is kind of hard to look at. So if it's easier to visualize, not a bad idea to drop the input parenthesis around that x, just to make it look a little bit less complicated. So now it has a common denominator. We can add across numerators. We maintain the same common denominator, 1 plus sine x times cosine x. That didn't really need parentheses like that. Let me write it in better. In this numerator, we can also just multiply these through. Cosine times cosine will give us cosine squared x, then plus. We might as well distribute this through as well. This is a lot of copying, and this can save some time. We'll get a sine x plus sine squared x. And that's progress. Remember, our goal is to get to secant x. We have to make a secant out of this somehow, some way. And at this stage, it's a huge mess. This is a portion where we probably need an identity to help us out. Anyone see a good purpose identity that we could use on this one? It's kind of hard to see for one particular reason on this one. I would say the reason the identity is hard to spot on this is because things are just mixed up in the numerator. So what you would want to visualize is, what if you put cosine squared up in front right here? That would have been a sine squared x plus cosine squared x. But sine squared x plus cosine squared x is automatically a 1. It actually doesn't matter if the terms are out of order. If you have a cosine squared and a sine squared somewhere, and this is all separated by addition, then this whole thing right here and right here, you could just drop in a 1 immediately. So that's the identity, the original Pythagorean identity. The moment you see a cosine squared or a sine squared or even both, that's the dead giveaway. You should be using this one to try to resolve the problem. So this is going to turn into, I'll just drop a 1 right here where the cosine squared was. And we've done it. That's the 1 from cosine squared plus sine squared, or sine plus cosine. Either order you write it, the effect is the same. Then it's plus sine x. I'm going to put a parenthesis around the numerator just for visual effect, because now we have an extra cancellation the moment we did that. There's also a 1 plus sine x in the denominator and a cosine x. But the new cancellation is, because everything is in a nice factored form in the denominator, that stuff cancels. We're left with just a 1 after cancellation. So this is 1 over cosine x. And that's the reciprocal identity for secant. Secant x is 1 over cosine x. Our work is done right at this step. So when it said write it in terms of secant x, in this problem, that's just how the entire thing ended. It could have been, again, 5 secant x, or it could have even been 1 over secant x. The only guarantee is that secant is going to be the only function left over when the dust settles. We did it, folks. This one's tricky because, again, we had to find least common denominators, add up the fractions, and it's hard to visualize this because you're doing algebraic topics that you could be a little bit rusty on, while navigating the mental noise of these aren't like x's and y's. These are huge functions like cosine and cosine. They still obey the same algebraic properties of cosine times cosine would be cosine squared and so on. And we're also having to navigate dropping in identities to assist the work at the same time. Trigonometric functions have lots of properties like these we can take advantage of. So this problem is now over at this stage. But the big takeaway from this problem is that we've done the following. we have shown that cosine x, 1 plus sine x, plus tangent x, this is just an extremely complicated way to write secant x. In other words, we have shown that this equation is an identity. And in place of the word shown, there's lots of things you could say instead. You could have said shown or verified, or you could say proved, and etc. Other things would be, I'm not sure of any other similar things, but anything that conveys these same ideas could be a different way to say the same thing. And I like the word proved because it reminds us this is a legitimate mathematical proof that cosine divided by 1 plus sine plus tangent is in fact secant. And that's just what we mean by an identity. This is always true for all values of that variable x that are in the domain of the right-hand side and the left-hand side at the same time. Well, any questions at all, folks, doing this simplification? Okay, we haven't used a lot of fancy identities. We've used this one a couple times in different forms. We've used reciprocal identities, or the fact that tangent, sine over cosine, secant is 1 over cosine, and so on. But keep in mind, there's a whole list of identities that are on the table. So we'll make sure to do at least a couple problems that involve this kind of stuff, this one or this one. They'll come up as well as we go through the rest of the chapter 7. So the next thing we're going to get into is, as the problems are kind of teasing on the end comments, we're really proving identities when we do this work, whenever we simplify and get something like that. And that's the whole goal on this one. Example 3 says, verify the identity, or it could have said prove the identity and so on. It starts with the rule, do not start by assuming the identity is true. We'll talk a little bit more about that when we come back on, let's say, Monday's class. That's where the topic about avoiding circular logic comes into play. So we'll discuss this in a little bit more depth, not on the last minutes of class today. So verifying the identity, in a certain sense, this is kind of like a nicer problem than even the last ones we've done. Think of what we did in problem part A, example 1, for example. On this one, we did in fact prove an identity that the left-hand side equals the right-hand side, but we had no idea where we were going with this. And some people might have ended in a different spot entirely and just found no way forward. It's in simplified form as possible. We just happened to stumble on probably the nicest simplification. The whole thing is sine x. So what the next examples are asking us to do is something just like that. We know where we're starting, we know where we're going. We're just trying to match up the left-hand side and the right-hand side. We can't start by assuming the identity is true by doing algebra on one side and starting to simplify down. If you did go that route, you have to reverse your whole set of steps to avoid circular logic. So here's another approach that we're going to take. We're going to denote LHS. This is going to be a common acronym we'll use when we verify identities. This will mean left hand side, or the left-hand side of the equation. So when you see LHS, that would be this side. This is the left-hand side. Then likewise, we'll use RHS to mean right-hand side. So that's the RHS. They'll just refer to the right-hand side of the equation. So that means this stuff, here to here. This is the right-hand side of the equation. And so now our method or strategy is to do one of the following. One method would be pick the left-hand side, start to simplify it taking the same kind of steps we were taking on example 1, part A. It could be a lot of steps. So this is us simplifying the equation until it ends up to the right-hand side. The moment you can link up one's part of the equation, do a whole bunch of algebraic simplifications, and it ends up as the other side of the equation, your work is totally done right at that stage. So that's one method. Another method is, let's call that 1 for method 1. Another method 2 would be start at the opposite side. It might just so happen that maybe beginning at the left-hand side is tough, or maybe it's just hard to see where to go. You might want to start on the right-hand side, maybe simplify that just right and things work out. So start on the right-hand side, the ... is the mathematical missing ingredients of simplifying, expanding on what should happen until you get to the left-hand side. So this is the simplify work. Same thing we were doing on the very last 3 problems. Sometimes strategy 2 works really well. Sometimes strategy 1 works really well. Another strategy, strategy 3, is to do the following. Write out the left-hand side until you get to something. So the start here is going to just be some algebraic expression involving trigonometric functions. And if we don't know what to do with that something, if we're just stuck, pick up the other end, the right-hand side. Start simplifying that down. And if it equals that intermediate something, if you end on the same thing on the left-hand side and the right-hand side, you can conclude, therefore, left-hand side is equal to the right-hand side. It's the same as 1 and 2, you just have a little intermediate thing. It's as if you're putting vertical equalities going this way, linking up in that direction. So these are the 3 main strategies. There's a 4th main strategy that we'll discuss in avoiding circular logic of doing something algebraically to this. If you go with that 4th strategy, the steps do have to be reversed. The reason is, if we're verifying this identity is true, you cannot start by assuming it's true in the very first place. That has to be your last step right here if you work with both sides simultaneously. So those are kind of the rules of the game. We'll do several problems to practice this. And really, the earlier problems that we did today were all just practice for this idea. Proving identities or verifying identities are true. It's kind of an art form. It's like some kind of giant puzzle that you're trying to resolve. And when it comes to doing these on homework problems, if you did assume that identity is true, you might lose some credit. I'll give you the opportunity to redo the problem to reclaim that credit. And also, if you get stuck on any one of these, don't hesitate to email, drop in during office hours, anything like that. I'll be happy to help out. I'm definitely happy and willing to give out hints on how to start them, strategies to use. You can show me the work you've tried and I can say, maybe you made a mistake here or point in a different direction to go. Okay, so that's a big spiel before we even started the problem. What I would do on this one personally is ignore the left-hand side, because if I was going to work on the left-hand side, I would be working with fractions. It's not hard, really. But to me, it's a little bit easier to work on the right-hand side, because I can just start simplifying that. I'm not working on fractions at all. So that's going to be my approach, starting with the right-hand side. This is how it indicate the work. Right-hand side, this is me starting off this method 2 right here. It's equal to a cotangent theta times a cosine theta. Now we just do something, we're in the middle steps here, the simplify. We do something to this to try to make it look like the left-hand side. But one thing we have for sure right out of the gate is that cotangent can be written in terms of cosines and sines. Cotangent is a cosine theta divided by a sine theta, and then just copy down times cosine theta from this part. We are still working with fractions, it turns out, but this we can multiply into the numerator to get cosine squared divide by sine theta. And here's where identity comes into play. By now, you're probably just expecting this. If cosine squared comes up, the very first thing you ought to do is just write down sine squared theta plus cosine squared theta equals 1. Now we can put something in place of, let's just use yellow there. We can put something in place of cosine squared just by coming down below right here and solving for cosine squared. Another way to write cosine squared is that it's equal to 1 minus sine squared theta. And that's going to be our swap. 1 minus sine squared theta is just going directly inside here. So now it's equal to 1 minus sine squared theta divided by sine theta. So again, we started on the right-hand side. This work so far is like the dot, dot, dots. We're simplifying things, but we have a target that we're trying to get to. There's a goal in mind. We're trying to get to this, that full left-hand side. And we're nearly there. Sine can divide into both these terms individually. So we can rewrite this as 1 divided by sine theta minus divide into the second term in the numerator, sine squared theta divide by sine theta. We're almost there. We still have a simplification to go. This is 1 over sine theta minus sine into sine theta squared just leaves us sine theta altogether. And that's identically the left-hand side. At this stage, the verification is totally complete. We started on one end, the right-hand side. We did a whole bunch of simplifications. We even had to cite a trigonometric identity in an alternate format. And then we ended up, let me say that differently. Got that backwards. We actually started on the right-hand side. Hang on. Yeah, right-hand side, which is, it's just messing me up, I think, because when I see this, I'm thinking left-hand side, but no, that's how we started. We started on the right-hand side, we did some simplifications, and we ended up on the left-hand side. Some reason my brain just wants to put left-hand side here because it's the left side. But no, that's the actual approach that we had took. Because all of these are linked up with equalities, we have shown by the transitivity equality that in fact 1 over sine theta minus sine theta is cotangent theta times cosine theta. At this stage, our work is complete right at that step. Well, any questions at all, folks, getting through to this stage? Okay, you might wonder, what is a context where you'd really need this? When does this really come into play later on in a math class? And I'd say this is something that does happen routinely in calculus 2 out of nowhere. If you're taking calculus, this kind of stuff is useful in calculus 1, but in calculus 2, it gets even more useful. It's almost as if the more calculus you take, the more kind of mathematics you take of just about any kind, the more trigonometry just keeps on coming back, and sometimes in this exact kind of way. It turns out in calculus 2, you do a process called integration. Integrating the right-hand side is trickier than integrating the left-hand side. So for a completely different process later on, if you're going to take calculus, this is something that you're going to be staring at down the line several semesters from now, or just a couple semesters from now. So that's one reason this is very useful. Another reason is equation solving. Sometimes one equation is easier to solve than the other. That's just a harder thing to see on this one. This one's a pretty random looking identity. Well, we'll try it again with this next one. Example 4, verify this identity. Then we'll try it again on example 5, the very next identity. This one in the middle turns out to be actually kind of hard. It is possible to start at one side and end up on the other, but I think it's not easy to see what the actual algebraic steps would be. So for this particular problem, this would be my go-to approach. Both sides are equally complicated looking, if you ask me. And I would start off by doing this. Take the left-hand side. We're going to do something to this algebraically. We're going to end up at something way out here. I don't know what the expression is yet until we go to attempt it. We're going to get to what looks like kind of a dead end. Unless you're very creative, you might find the way out of this. But if this happens in the homework, if you're not sure what to do next, we'll also pick it up on the right-hand side, work it out a bunch. And if we get to the same exact expression, working both sides of the identity simultaneously, if we end up on the same thing, our work is done. So I think this one is easiest to do in that kind of strategy. Work independently, try to come up with a common expression, and the moment you find it, the work is over. Well, I'm looking at the clock, and I've got about 4 minutes to do this one. This one's harder than the last one, and these are pretty big, chunky problems so far. So I think this is a good one to take a bit of a mental break on. We'll attack this one in full when we have the time and mental energy to really get through it on Monday's class. We'll also spend a lot of time going through this one, talking about the need to avoid circular logic, why we can't start by assuming an identity is true, why we really have to work by something we already know is true and end at the identity. So this one we'll save for next time. But any questions or comments at all, folks, before we end class a few minutes early? Okay, well, it's been fun, folks. We'll take a bit of a breather on this one. I think it's only fair. We got through exam 2 as well. And we'll be getting into section 7.1, 7.2 when we come back on Monday's class. But have a nice weekend, folks. Watch out for your IUCU email. I'll be great sending your graded exams back to that email address. But have a great night. I'll see you all next week.
Thank you.
You bet. Yeah, absolutely. I'd be happy to help out. Let me make sure to end the recording.